So we have been looking at electrophilic aromatic substitution reactions, and let us talk about the Friedrich-Krauss alkylation. Remember, in the Friedrich-Krauss alkylation, you're replacing one of the hydrogens of a benzene ring with an alkyl group. The benzene ring being the nucleophile, while the alkyl group is the electrophile. Now, this reaction doesn't just proceed by itself. It needs the help of a Lewis acid. And the Lewis acid that we're talking about is mostly things like aluminum chloride, right? So if you have something like sec-butyl chloride, in the presence of aluminum chloride, you have a substitution. See, you have a substitution to give you the arene. You can see that the Lewis acid helps to activate. It helps to activate the electrophile. It makes the electrophile really desperate for electrons, and as a result, this substitution occurs. As you can see here, because aluminum has an empty 2p orbital, it's able to accept electron density, and that makes the chlorine electron deficient. It now has a positive formal charge, and that leads to the breaking of the carbon-chlorine bond to yield the carbocation, which is then the electrophile, as you can see. Now, primary carbocations are too unstable to form, yet primary alkyl halides can react under Friedrich-Krauss. As you can see here, the reaction of benzene with butyl chloride or chlorobutane yields butyl benzene, as well as this arene. Okay. Now notice that in this product you can see that this has undergone a rearrangement. First, the alkyl halide reacts with the Lewis acid, as you can see. That leads this activated complex, and this is where the electrophile is generated. And once the electrophile is generated, then the reaction continues. But notice that because a primary carbocation is less likely, a hydride shift occurs. You have an hydride shift occurring to give the secondary carbocation. And the secondary carbocation now reacts with the benzene nucleophile to yield the substituted benzene. Now, we might expect the hydride shift to occur more readily than the direct attack. That's because, remember, a secondary carbocation is greater in stability than its primary carbocation. Okay. Now, a reaction in which you have mixtures of products is not practical because you have to do a lot of separation. You have to carry out separation, and of course, that reduces the yield. It reduces yield significantly. You see, there are three major limitations to the Friedrich-Krauss alkylation. The first is the halide leaving group must be attached to an sp3 hybridized carbon. And of course, you know by now that these reactions go SN2, SN1. Okay, and so if you have a compound in which the chlorine is attached to an sp2 hybridized carbon, you know that the reaction cannot go SN2 or SN1. And so the Friedrich-Krauss acylation is limited to halide groups that be attached to an sp3 hybridized carbon. The other thing you have to remember is that polyalkylation can occur, just like when we did the alkylation of 1,4-dimethoxybenzene. You can notice that we got the dibutyl incorporation. Okay. And the other thing is that some substituted aromatic rings, such as nitrobenzene, they are too deactivated to react, and so no reaction will occur. See, because of the presence of this strong electron withdrawing group, most of these reactions are very difficult to occur. Now, acylation and alkylation both form a new carbon-carbon bond. They both form a new carbon-carbon bond, right? So if you did an acylation and alkylation, you are forming a new carbon-carbon bond. Now, the acylation, just like alkylations, are also generally catalyzed by Lewis acids. See? So instead of incorporating an alkyl group, you can incorporate an acyl group by using, say, acyl chloride, the presence of a Lewis acid, aluminum chloride, to yield the substituted product, right? And then you can easily remove the carbonyl group by a simple reduction. You can do a carrier-to reduction, an appropriate reducing agent, which we are going to talk about, and you get the arene. Okay. Now, one good thing about this is that this reaction proceeds through an acylium ion. It proceeds through an acylium ion, and this is not prone to rearrangement, does not rearrange. It does not rearrange, and because it does not rearrange, it yields just one product. Okay, so you don't have multiple products. Now, the reason why it doesn't rearrange is because, of course, the acylium ion is resonance stabilized, and as a result, it does not rearrange. Okay. Now, some alkyl groups cannot be attached to a ring by Friedrich-Krauss acylation because of rearrangements. And isolation followed by Clemmensen reduction is a good alternative. So, something like this, if you are going to make something like this, right, because this involves the attachment at the primary carbon, this would be require the attachment at a primary carbon, because prior to that, what you had was something like this. You had this. Now, this is a primary carbon. If you're going to have attachment at that primary carbon, it's not going to be possible, because what's going to happen is rather than have this product, you're going to have this product. You see, you're going to have this product. That's what you're going to have if you did the Friedrich-Krauss alkylation. See, they're going to get that product. So to get strictly this product, the best way to go about it is to do an acylation, in which case you get this, and then the presence of Clemmensen reduction, you can reduce the carbonyl to the alkyl group. You can also do it under basic conditions, in which you can use hydrazine in potassium hydroxide and heat, and this gives you the Wolff-Kirchner reaction. Right? Or you can do a reduction with palladium and hydrogen, and that's under neutral conditions. So that's a way of getting rid of a carbonyl group. Okay, it's a way of getting rid of a carbonyl group. But you see, these carbonyl groups have to be in the benzylic position. Unlike polyalkylation, as polyisolation is not generally observed. That's because once you introduce the acyl group, this ring becomes deactivated. There is deactivation of the ring, and so it's not prone to polyalkylation, because upon incorporation of an acyl group, the ring becomes deactivated. That means the ring becomes unreactive. Substituted benzenes may undergo electrophilic aromatic substitutions with faster rates than unsubstituted benzene. What's the rate? Of course, we know the rate is the change of reactants per unit time. Okay, over time. How does the concentration of the reactant change over time? Okay, so the change of the reactant, say reactant A, over a given time T. Okay, so it's delta A over delta T. Now, toluene undergoes nitration 25 times faster than benzene, and that's because the methyl group on the toluene activates the ring towards induction. And of course, you know by now that alkyl groups are electron releasing. They release electron density via hyperconjugation. Now, substituted benzenes generally undergo electrophilic aromatic substitution radioselectivity. You see, they actually undergo electrophilic aromatics substitution with a great deal of radioselectivity. Notice here that the auto is formed with 63%, the para is 34%, but the meta is barely formed in only 3%. To be able to understand why this reaction goes this way, we have to look at the nature of the arrhenium cation that forms upon addition of the nitro group. See, we have to look at the formation of the arrhenium cation that forms, or the sigma complex that forms upon addition of the nitro group. As you can see here, upon addition of the nitro group, the carbon bearing the methyl group is positively charged, and because it is positive charge, it's significantly stabilized by the electron releasing effect of the methyl group. Okay, and of course, if you draw resonance, you can see that the positive charge is never connected to the carbon that is attached to the electron withdrawing group. It's always on a different carbon. So if the ring attacks from the auto position, the first resonant contributor of the sigma complex is stabilized. See, it's stabilized how? How is it stabilized? It's stabilized by hyperconjugation. See, it's stabilized by hyperconjugation. You can see here, you can see that the positive charge is connected to the alkyl group. And of course, alkyl groups are electron releasing. It releases electron density to the positive charge on the carbon. And as a result, because of the stabilization of this intermediate, we can see that the transition state will be lowered significantly, and that gets the activation energy much lower and gets the reaction going in the forward direction. But if you look at the meta attack, you see, with the meta attack, you notice that the positive charge is never on the carbon that is connected to the electron releasing alkyl. See, the positive charge is never attached to the carbon that is attached to the electron releasing alkyl group. On the other hand, if you look at the para attack, the positive charge is stabilized by the electron releasing effect of the alkyl group. You can see that, and that leads to a significant lowering of the energy of the sigma complex. So I want you to make a note of that, and that's why something like toluene is supposed to be an auto para director. You can see that the activation energy for the auto and the para is much less than the activation energy of the meta attack, and that's why the reaction goes exclusively auto para and not meta. Okay, the same thing is true for the methoxy group in anisole, which activates the ring 400 times more than benzene through induction. You see, the methoxy group is electron withdrawing. Okay, but we'll continue from there in the next slide.